Good morning, Vietnam. This is Lab 4. My name is Jake Bernstein, and I'm about to take you on the ride of your life, walking you through this lab on oscillations. Now, today I'll be presenting the results of our physics lab experiment on oscillations, specifically focusing on a spring mass system. This presentation will showcase how our observations align with theoretical predictions. Now, the purpose of the experiment was to observe the motion of an oscillating object, which is a system consisting of a spring and a mass, and compare these observations with the motion predicted by a computational model. Additionally, this experiment aims to demonstrate the energy principle and Newton's second law. It's essential to confirm that our models align with physical observations, as this validates both the energy principle and the computational techniques used. Before diving into the experiment, let's review some essential concepts: Newton's second law and the energy principle. These principles govern the behavior of oscillating systems and form the foundation of our analysis. Newton's second law relates force, mass, and acceleration, while the energy principle helps us understand the exchange between kinetic and potential energy in the spring mass system. Now here we show the primary formulas used for analyzing the spring mass system. These include Hooke's laws for spring force and equations governing energy transfer in the system. Understanding these formulas is key to following how we derived our predictions. Next up, we have our experimental setup. Now, our system consists of a spring, a mass, and the Earth. We assume an idealized environment for ease of our calculation. Now, we set the initial position and velocity to 0 and use values such as gravitational constant, spring constant, and other specific measurements for this computation. It's important to note that even though we assume an ideal system, there will be external factors such as air resistance that could slightly alter our results. Here we have our tracker analysis, in which we use tracker software to analyze the motion of the spring mass system, and the software helped us capture and track the oscillations frame by frame, providing precise data to graph position and velocity over time. And then next up we have our computational model code, and these slides show the code we use in our computational model, starting off with establishing L hat, moving on to computing the energy, kinetic, and gravitational, as well as spring force. And then we've established a loop to further help us understand the energy transfers and the forces acting on the system. Here's just an extension of the code in which we find K, delta K, gravitational potential, delta gravitational potential, and then use that to calculate our spring constant. Here is a video of our tracker. I'll play that for you guys. It's super satisfying just seeing the red thing swirling and swirling. Alright, moving along, you get the gist of that. Here is a graph of delta energy, and here we present the graph showing the change in energy over time. Now, notice how the total energy remains constant, aligning with our energy principle, and we'll have an analysis of that later on. And this consistency confirms that our model accurately represents the conservation of energy within an ideal system. Now here are our graphs of the observed versus predicted position. And in this graph, we compare the observed motion from tracker with the predicted motion from the model we created. And the close alignment between the two confirms the accuracy of our computational model. The one on the left is the y-axis, one on the left is the x-axis, one on the right is the y-axis. Now, when experimental results and model predictions align closely, it strengthens our understanding and application of the physical laws that govern the system. Next up, we'll have potential error. The two errors I wanted to focus on were human error, centered around the imperfections we had when placing the center of mass using tracker. And then the second one is the system is not entirely isolated from its surroundings, meaning there will be some external work, and the total energy is not equal to 0. Next up, we have our conclusion, and in conclusion, the energy principle was satisfied as the changes in kinetic and potential energy balanced out, confirming that the total energy of the system remained 0 when no external work was assumed. Now, this experiment effectively demonstrates how theoretical models and principles and physical observations can align, further validating Newton's second law and the energy principle. Now, to wrap it all up, we have a discussion. And one interesting observation was that using different coordinate axes produced varying results when calculating the period of oscillation. And now this means that the variability impacts the spring constant and the relaxed length of the spring. And this highlights the importance of choosing the correct reference frame when analyzing a physical system. Thank you very much for watching. I hope you